Hi everyone. Today we're going to learn about implicit differentiation. And before we jump right in, let's recall our favorite technique of differentiation, namely the chain rule. Suppose we want to differentiate f of g of x. How do we do it? Well, we know that it's going to be the derivative of f of stuff, right? This is how we talked about it. The derivative of this is f prime of stuff times the derivative of what's inside. And what's the derivative of the inside function? It's g prime of x, assuming everything's differentiable, of course. And this is the chain rule. Everybody's favorite. Well, let's do something that seems silly here but will be useful for us later on. Let y equal to g of x. Notice that on the right hand of the equation I have x's, but on the left hand I don't have x's. So whenever we just see y, we're implying that y is a function of x, right? Y is implied to be a function of x. So let's differentiate something that is pretty much the same. Let's differentiate a function f of y with respect to x. And this seems strange, but remember that what is y? Y is a function of x. So we're going to treat this exactly the same as we did with the chain rule. We're going to cover up what's inside, and we're going to say, boy gee howdy, what is the derivative with respect to x of f of stuff? As always, it is f prime of stuff, right? And now we need to multiply by the derivative of what's inside with respect to x. And what's the derivative of what's inside with respect to x? Well, it's the derivative of y with respect to x. That is dy dx, right? And it looks funny, but that's exactly the same as what the chain rule says. And in fact, what's y? It's g of x. And what's dy dx? That's g prime of x. And so these two things, these two statements here, are exactly the same. And this is called implicit differentiation. This is called implicit differentiation. Sorry about my handwriting. Where we want to differentiate a function of y with respect to x. And y is implicitly defined, so it's implied, as a function of x. And that's kind of cool. So this is going to be particularly helpful where we have an equation, but you can't explicitly solve for y. Not all equations you can solve for y, it turns out, and we'll see examples of that today. So let's do a quick example. How do we differentiate? Let's do a non-example and see how our technique that we've been doing over and over again, we're going to generalize this. Let's differentiate our favorite function, y equals x divided by 1 plus the sine of x. And suppose we want to find dy dx. How would we go about doing something like this? Well, we need to differentiate both sides. All that we're going to do is differentiate both sides with respect to x. Okay? So we differentiate the left-hand side with respect to x, and we differentiate the right-hand side with respect to x. And what do we get? What's the derivative with respect to x of y? Well, that's dy dx, right? Equals, what's the derivative of this quotient with respect to x? We need the quotient rule. And so we get low d high minus high d low, draw a line square below. And that's all there is to it. We have now found dy dx. But what was the strategy that we're going to use? We're going to differentiate both sides with respect to x, and then solve for dy dx. In this case, there wasn't anything else to do because y was the only term on the left-hand side. But let's see how this can be a little bit different. Let's consider another example. Suppose we have the equation x squared plus y squared equals to capital R squared, where capital R is a constant. And as everybody's hopefully remembering from pre-calculus, this is just the equation of a circle centered at the origin with a radius r. How could we find dy dx? How could we find dy dx? Well, I know what you're thinking. We can solve for y, right? If we solve for y, we would get that, well, y squared is r squared minus x squared. So square rooting both sides, we get that y is plus or minus the square root of r squared minus x squared. And this isn't a function. It's not even a function. So if we wanted to find dy dx of this guy, we would have to do it separately depending on what the value of x is. And that seems not optimal. So let's instead find dy dx using a method that we don't actually have to solve for y, and it's kind of cool. What's the strategy? Just like up here, we're going to differentiate both sides of the equation with respect to x. Okay? And let's do it. We're going to compute the derivative with respect to x of the left-hand side and the derivative with respect to x of the right-hand side. How do we do that? Well, what's the derivative with respect to x of 2x? I just gave it away, sorry. What's the derivative with respect to x of x squared? It's 2 times x times the derivative of what's inside with respect to x. And what's the function inside the square? It's just x. So I'm going to write it really funny, and you'll see that it's the same. And what's the derivative of x with respect to x? That's 1, right? But we'll see that this idea is exactly the same as what we're about to do in the next term. What's the derivative with respect to x of y squared? Well, what's the derivative of stuff squared? It's 2 times stuff, times the derivative of what's inside with respect to x, which is times dy dx, equals, what's the derivative with respect to x of our constant r squared? That's 0. Yeah? And so now, what's the derivative of x with respect to x? That's just 1. So we have 2x plus 2y times dy dx. dy dx doesn't simplify. And that's 0. And now, we can treat this like an algebraic equation. And we can solve for dy dx. dy dx, we first subtract 2x, and then we divide by 2y. And then dividing the 2's, we get negative x divided by y. And that's kind of cool. But I know what you're thinking. Let's talk about this for a few more seconds. Oops. In the equation, let me write the equation again, x squared plus y squared equals to r squared. This is a circle. Yeah? And the radius is r. And I know we've just now shown that dy dx is equal to negative x divided by y. And what happens if y is equal to 0? Well, in our graph, what's happening whenever y is 0? At y is 0, that's on the x-axis. So if y is 0, we know our circle is straight up and down. And indeed, the circle has vertical tangents. At y equals 0. How can we see this in the derivative? What's happening whenever y is 0? We get that dy dx is, of course, undefined. And it goes towards infinity as you approach 0, of course, since we're dividing by 0 there. And so we see that this derivative tells us that we have our vertical tangents at y equals 0, which is kind of nice. All right, let's do another example. Find the slope let's see, find the equation of the line, and the word that we have now, we're gonna have a new word, normal. Normal. And the word normal means perpendicular. So anytime that you see the word normal, it just means perpendicular. Find the equation of the line perpendicular to the curve y squared equals x cubed plus 1 at y equals 3. And this looks kind of funny. Find the equation of the line perpendicular, or normal, to the curve y squared equals x cubed plus 1 at y equals 3. Well, before we do this, let's recall. If we have a line that's perpendicular to a curve, it has to be perpendicular to its tangent line, right? So let's draw an example. If our curve looks like this, the way that we're going to construct the slope of a normal line is to construct the slope of the line normal to the tangent line. So here is our line tangent to the curve at some point. And our normal curve will be perpendicular, or normal line rather, will be perpendicular to the tangent line. So, if the slope of the line tangent to f of x at x equals c is m equals f prime of c. Let's remember from algebra, what will be the slope of the line perpendicular to f of x at x equals c? Well, remember, the slope of the line perpendicular to f of x is really going to be perpendicular to its tangent line. So what's the slope of a line perpendicular to another line? Remember from algebra we said that this was I think we probably used the word negative reciprocal or something along those lines. And indeed, in this case, it's -1 divided by f prime of c. Yeah? And this is the slope of a perpendicular line to a function at a point. Let's see how to use that to solve this problem. How do we find the equation of the line, of the normal line, to this curve at this point? What do we need? We need a point and a slope. So let's go on the hunt. Let's go on the hunt. What's the point that we have? I know that y is 3. How do we find x if y is 3? I know that y is 3, so 9 equals to x cubed plus 1. So what does x have to be? X has to be 2. So here's our point. How do we find the slope of my normal line? Well, first we really need f prime of c, right? Once we find the derivative at c, then the slope of the normal line is the negative reciprocal. So really we need to compute dy dx. We need to find, first and foremost, dy dx. So here I want you to pause the video, try to find dy dx yourself. You have all the tools that you need right now. Give it a shot. Okay, so to find dy dx, we're going to differentiate this equation with respect to x on both sides. So we have d dx of y squared equals d dx of x cubed plus 1, right? And what's the derivative of the left-hand side? It's 2y times the derivative of what's inside, which is dy dx. And this is equal to the derivative with respect to x of x cubed plus 1, which is just 3x squared. So, let's solve for dy dx. We have now that dy dx is equal to 3x squared divided by 2y. And at the point 2, 3, dy dx, evaluate at 2, 3, should be, well, let's plug in x equals 2 and y equals 3. We get 3 times 4 divided by 6, which is 2. So what's the slope for our normal line? What's the slope of our perpendicular line? It's the negative reciprocal. M is negative 1/2. Negative 1/2. Sorry about that. So now we're ready to make an equation of a line. We have y minus 3 equals negative 1/2 times x minus 2. And that's not too bad. That's not too bad. Let's do another example. If y times the sine of x is equal to x times the sine of y, find dy dx. And before we jump right in, note that we can't solve for y explicitly as a function of x. We need to differentiate implicitly because we cannot solve for y explicitly as a function of x. So pause the video, try to do this yourself. The strategy is the same. Differentiate both sides with respect to x, and then solve for dy dx. Give it a shot. All right, so we're going to jump right in. We're going to differentiate both sides with respect to x. Here, y is a function of x. It's implicitly defined as a function of x. Sine of x is a function of x. To differentiate, we need the product rule, right? Similarly, on the right-hand side, we will need the product rule to differentiate this. So we need the product rule. Let's do it. It's the first, on the left-hand side, it's the first times the derivative of the second plus the second times the derivative of the first, which is dy dx, equals. On the right-hand side, product rule is the first times the derivative of the second. But remember, whenever I differentiate sine of y, I'm really differentiating sine of stuff. So I get cosine of stuff, but now I need to do chain rule times the derivative of what's inside, which is dy dx, plus the second times the derivative of the first, and the derivative of x with respect to x is just 1. And now we want to solve for dy dx, right? How do we do that? It's just an algebraic equation now. Here's the dy dx. Here's the dy dx. The strategy, of course, from algebra, get all the dy dx terms on one side, get all the other stuff on the other, factor and divide. Okay? So let's move everything with a dy dx to the left. Let's move it to the right-hand side, I guess. No, we'll move everything with dy dx to the left-hand side. Everything else can go to the right-hand side. It'll be fine. So we have sine of x times dy dx minus x cosine y dy dx equals to sine of y minus y cosine of x. So we subtracted the terms with dy dx's to the left-hand side and subtracted the term without a dy dx to the right-hand side. On the left-hand side, we're now going to factor out dy dx and divide by what's left over. Whenever I factor out dy dx, on the right-hand side, I will still have sine of y minus y cosine x. But what will I divide by on the left-hand side? We'll divide by sine of x minus x cosine y. And that's not so bad. And that is dy dx, and it doesn't look fun or nice, but it is what it is, right? Let's do another example. Let 2x squared plus 3y squared equal to 1. And let's find d squared y dx squared. Remember, this is the second derivative of y with respect to x. And remember, we defined this in the last video as d dx of dy dx. So what's step 1? We need to find dy dx, don't we? And then we need to differentiate again. Let's do it. How do we find dy dx? Let's do that first. Well, we need to differentiate both sides with respect to x. Pause the video, give it a shot. You have all the tools that you need. All right. So differentiating the left-hand side, it's going to be 4x plus, what's the derivative of 3 stuff squared? It's 6 stuff times the derivative of what's inside with respect to x, which is dy dx, equals to the derivative of 1 is 0. And solving for dy dx now gives us that dy dx is equal to negative 4x divided by 6y, which is negative 2x divided by 3y. And that's not so bad. But we're not done, because the question was asking for d squared y dx squared. So we need to take the derivative again of this function with respect to x. So let's do that. Differentiating the left-hand side gives us immediately d squared y dx squared. And now we need to differentiate negative 2x divided by 3y. And once again, you have the tools to do this. Pause the video, give it a shot. All right, so first I see a quotient of two functions. Let's use the quotient rule. So I see that this is going to be low d high minus high d low. And what's the derivative of y with respect to x? It's just dy dx. Draw a line and square below. But I know what you're thinking. I have an x, I have a y. Dy dx is something different. But I know what dy dx is because we already solved for it, right? Let's plug it in because we just want this with x's and y's. So we can simplify this a little bit. We see that this is negative 6y plus 6x times negative 2x divided by 3y, all divided by 9y squared. And let's keep simplifying. Let me move the video down, sorry. Let's simplify this a little bit more. This is equal to negative 6y minus 4x squared times 1 over y divided by 9y squared. And we could stop here, but there's something really cool that's going to happen if we multiply by our favorite one, y divided by y. Yeah? And we're not going to introduce any new division by 0 because we already have to throw away division by 0 whenever y is 0, right? So let's multiply by y over y and see what happens. We get negative 6y squared minus 4x squared divided by 9y cubed. And that doesn't look helpful, does it? But I know what you're thinking. What was my original equation? My original equation, let me write it over here, was 2x squared plus 3y squared equals 1. And that's almost the same as this, it turns out. Let's multiply this equation by negative 2. If we multiply this equation by negative 2, we get negative 2. Well, I'll be consistent. We get negative 4x squared minus 6y squared equals negative 2. And here I see negative 6y squared minus 4x squared. So that quantity must be negative 2. So this fraction simplifies to negative 2 divided by 9y cubed. That's kind of interesting. So I hope that you enjoyed this video. If you have any questions, feel free to reach out and we can either figure out your problems via email or we can set up a time to Zoom. And I look forward to seeing you in the next video. Thanks so much for watching.